cone's not what you see in an ice cream shop, but it's got two branches and goes on definitely both directions. And if I were to take a plane in this room and take a cross-sectional slice of the cone perpendicular to the ink board, but also perpendicular to the central line of symmetry, what kind of geometric shape will it generate? I agree. If, however, I come in still perpendicular to the ink board, but slightly not perpendicular to the central line of symmetry, I think that shape is continue to be perpendicular to the ink board, but parallel to one of the original lines I used to create this cone. This is going to be a... I'm sorry, I just didn't hear you. I agree. And of course, that plane is parallel to the central line of symmetry. I cut into both branches of my cone.
Hyperbola.
It's going to be a hyperbola. I agree. And for that reason, I sometimes refer to these as my conic sections, because they're two-dimensional cross-sectional slices of the cone. Well, at least they're my non-degenerate conic sections. I do have some degenerate conic sections, like a point, a line, or maybe two lines. But you guys, you're already masters at creating equations of conic sections in rectangular form. I just want to do things slightly different today. Now, when you guys study conic sections back in pre-calculus, you probably talked about the eccentricity of which one though? What an ellipse? But I want to talk about, well, in your trigonometry class, you're right, you probably talked about all of them. But most pre-calc classes just one.
Sorry.
But that's okay, I want to do what you're doing. I think all these conic sections could have something called an eccentricity. As a matter of fact, may I? I'll define the eccentricity as nothing more than the ratio of the distance between any point in my conic section. I know it doesn't look like one, I'm trying to be generic. Pretend this is a graph of one of my conic sections. Imagine one of the foci is located at the origin. I'll define eccentricity as a distance between a point on the curve and that focal point. In my picture, I guess it's between P and F. Over the distance between, I don't know, how about P and the line of directrix I'll call L. This is my line L, whose equation is x equals D. Now let's see what would happen if I try to rewrite this equation in terms of polar coordinates. Because I think in my picture, another name for the distance between P and F, I can interpret as R. Well, if I think of this as my x distance and my y distance to get to that point, here's the angle I make, I can think of that as a radial distance to that point from the origin. And so I think another name for my numerator is just simply that. I do think, however, when it comes to this denominator, the distance between these 2 points, isn't that this distance minus this one? So my picture, I guess it would be D minus X. Well, you know what? I don't like that. E may be a constant, D may be a constant. Now I got polar portions of points and rectangular portions. I don't like it. I want everything in terms of polar coordinates. So if you guys don't mind, I'll make a substitution. Let's see, replacing x with, what's the alternative name? Using my right triangle trigonometry. Isn't it the case that r is just, excuse me, I misspoke. Yeah, x is just r times the cosine of beta. I'll make a substitution. I said r times the cosine of beta. And if I were to clear fractions, I guess that gives me this. If I were to try to solve for r in this equation, I guess that gives me this. Actually, I have no idea what it gives me. Is that an ED over 1 plus E cosine theta? I think that would be the standard form of a conic section, given that the directrix is vertical in the right-hand plane and on one of the foci is at the origin. I admit if the directrix were in the left-hand plane, I get a sign change. Or if the directrix were horizontal, upstairs or downstairs, it'd give me a sign expression instead. I'd generate one of these 4 equations.
Sorry, how did you go from step 4 to step 5 again?
I did this in my head. I added this to both sides.
Okay.
Factor out an r, divided both sides by 1 plus E cosine theta.
Oh, I got you.
And I simply ended up with that ratio. I just did a lot of math in my head.
Could you spell with D minus X?
You know, my picture is just straightforward. D d minus x is just this horizontal distance.
What does that mean?
Well, I was defining the eccentricity as a ratio of this distance to this distance. And so that's just my man-made definition of eccentricity. I was just re-representing, this distance as this big distance, which is d, minus my x. And that's exactly where the phenomenon came from. Nothing more. And I also maintain, technically speaking, with this relationship, that I'm going to get a conic that has different qualities depending what e is. Now, I admit, from your definition back in pre-calculus of trigonometry, if these two distances are the same, in other words, if e is equal to 1, I think for free, I get a parabola. I think if e is less than 1, if I have time, I'll prove this to you, I get an ellipse. And I think if e is bigger than 1, I generate a hyperbola. And so do you guys think I can give you just 3 concrete examples, one of each, and impress upon you, if you've never seen this before, how easy it is to graph conic sections when they're represented in polar form. And I maintain this is so darn easy, it's just a bit of number crunching, nothing more. So examples. Here's my first. Question. Sketch the polar graph of this equation. I do think my equation is in one of these 4 standard forms. The first term downstairs is a clean 1, so I'll identify what the eccentricity is. In this example, e is equal to 1. I know I got a parabola. And a parabola has only one focal point. And if one of these standard forms gives me a conic section with a focal point at the origin, my only focal point is at the origin. And to scratch this parabola is as easy as just plotting the 3 intercepts, and you are completely 100% done.
Did you forget the e on the equation term?
I certainly did, Randall, thank you. Did you guys see what he's saying? Forgot the coefficient of e on the outside. My apologies. So, let's graph. Here's my x-axis. Here's my y-axis. Let me unitize the cat a bit. Planting my feet at the origin. If I look in the direction of either 0 or pi radians, wouldn't you guys agree the sine of 0 or the sine of pi is just 0? And so looking in either one of these 2 directions from the pole, I think this becomes a 0. My radial distance is just 3. I've got 2 x-intercepts, one here and one here. I'll even plot them for you. There's my 0, I meant 3, 0. And here's my pi. But walking 3 units in that direction. I have a tendency to use brackets instead of parentheses for polar points. If I stand at the pole, look straight at the positive y-axis, I'm looking in the direction of pi halves. But when I plug pi halves in for theta, the sine of it is just 1. 1 divided by 1 minus 1 is just 0. I think the corresponding radial distance is 3 divided by 0, which is undefined. So when I plant my feet at the origin, look straight up the y-axis, there's no radial distance. There's no corresponding point in the curve. When I look in the direction of negative pi halves, that's down the negative y-axis. I said negative pi halves. That's correct. Or you could have said 3 pi halves, either way. I think this value is negative 1, so the ratio becomes positive 3 halves. And so looking down the negative y-axis, I'm going to walk 1.5 units. And so I guess that's the location of the point, 3 halves, comma 3 pi halves. But since the focal point, the focal point, has to be at the origin, I guess I'm done. I think for free, my parabola has to look something like this. Come on, you guys, give me some feedback. I'm serious. Isn't that a piece of cake? I'm hoping so. So my second example, is that another parabola? I asked. My second example, is that another parabola? But is it one of my standard forms?
No.
What do you mean no? Why not?
Because that 2.
Okay, so the first term downstairs is not a nice clean 1. If you guys don't mind, I'll change it. I'll multiply both sides, or excuse me, top and bottom by 1/2. Now the standard form, the eccentricity is less than 1. And Therefore I get an ellipse. And here too, you guys, I'm serious. Watch how easy this is. X-axis, y-axis. If I look in the direction of pi halves or 3 pi halves, cosine 0. The radial distance is just 3 halves. There are 2 y-intercepts. If theta is equal to 0, looking straight at the polar axis, the cosine of that's going to be 1. I think r becomes just positive 3. And I think if theta is equal to pi, well, its cosine is negative 1, it's just going to give me 3 over 3. That's just positive 1. You guys okay with my points? And so my parabola probably looks something like this.
That's not a parabola.
Oh, that's
No.
I meant ellipse, sorry.
Pear.
Okay.
Does that look like an ellipse?
No, it looks like a pear.
Yeah, it looks more like a pear. I think I'm way off, because I think with an ellipse, I think there's symmetry with respect to its vertical axis. All right, I blew it. I guess to be clear with my picture, I need to show symmetry both horizontally and vertically. I think it'll look more something like this. Okay, you guys, this time I really can't draw.
That's a lemon.
Ukulele.
Whatever you want to call it. I got my vertices. One vertex is here. I think another vertex is here. But I think one focal point is here. But you give me the location of the other one. Give it to me in the total coordinates.
R 2 0 0.
Yeah, 2 comma 0, or maybe 2 comma 2 pi, same thing.
The focal points. Remind me again how you get those.
Actually, I'm not going to remind you how you got them back in pre-calculus. I think it was a bit of work. It was looking at an equation like this.
No, thank you.
I just think you don't need any of that garbage for this reason, David Watch. These standard forms don't even exist unless I assume a focal point is at the origin. And since the distance between this focal point and this vertex is 1 unit, then I know from the other vertex I'll go in 1 unit to get the other focal point. I cheated. I didn't look at any
So
analysis.
it's the same thing on the parabola as well. 0 0.
You know what? You're right. I could have been more clear to the reader. But again, since there's only one focal point, I think it's for free.
Yeah. Okay.
Well, jeepers, you guys, the only third example I need to give you is one of a hyperbola. Let's do it. I think, like the other 2 examples I just gave you, life is so easy in that all I need to do is take a peek at intercepts, so here I go. If theta is either equal to 0 pi, the sine of those angles is 0, I think the radial distance is going to be 3. Here are my 2 x-intercepts. I think now taking the remaining 2 angles one at a time, looking straight at the positive y-axis in the direction of pi halves, its sine is 1. This fraction becomes 1 itself. However, if I look straight down the y-axis, that's looking in the direction of 3 pi halves, above my fingertips is negative 1. I think I get negative 3. Let me say it one more time. Look in the direction of 3 pi halves, I'm going to walk negative 3 units. That means I'm walking backwards. So what do you guys think? Something like this? No, I'm way off. Remember, here's a focal point. I think for free, if a focal point's at the origin, that means I got to wrap around it hyperbolically. I think I must look something like this. Just relative to what you guys know about hyperbolas. And therefore, I guess, I'm going to do something like this. There's a rough sketch of that graph at this particular hyperbola. Let's just find all the other information. Yeah, actually, since these are my vertices right here, a vertex at, I don't know, is that 3 in this direction? And my other vertex is at 1, same direction. If there's one focal point, where's the other one? 4 comma pi halves. You happy? I asked. Are you happy?
Where's the calculus?
It's pretty easy.
Yeah, I know. Where's the calculus? Are you happy?
So
Yeah.
5
No.
questions like this on our test?
Yeah, right. No, you don't have to, because I'm missing the, I'm missing the,
Calculator on
no, true, I can do that, I can play calculus. I'm really missing the,
Asymptote.
asymptotes. And since I'm missing the asymptotes, let's talk about it. Would you guys not agree the asymptotes have this quality? Stand at the origin, look in the direction of the asymptotes, there better not be a corresponding R value. Oh, no. Shoot. I'm making these up out of thin air, you guys. I didn't realize my numbers are so nice. So let's talk about when R is undefined. It's undefined when my denominator is equal to 0, isn't it? And my denominator is equal to 0 when the sign is equal to -1/2. But sine of theta is equal to -1/2 simply when the angles are, I don't know, how about negative pi, is that 6? And positive 7 pi 6? Oh, but shoot. The asymptotes are going to actually pass through the center of this hyperbola, so I think with my purple pen, they're going to look something like this, if I can be that sloppy. And if you guys don't mind, I'd like to create the rectangular equations of these asymptotes. And if I'm going to do that with my mathy skills, I better pull out my point slope formula. So I got to confess, you guys, I'm creating the rectangular, not polar equations for these asymptotes. Both these purple asymptotes pass through the point 0, 2. So I'll substitute 2 in for y sub 1 and 0 for x sub 1. Now I just need m. But isn't m just a tangent of an angle? And if I looked at the positive pi 6, well, isn't this tangent just 1/√3? And I guess the other one would have a negative slope. So I guess the equations of my two asymptotes in rectangular form are going to be, is that 1/√3x? Ah, jeepers, how easy. And likewise over here with a negative slope but the same y-intercept. And you guys see how my 3's magically become 2's? It's nice.
Amazing.
That happens.
So where'd you get the 1/√3 again?
It was this easy. I think R is undefined when theta is equal to pi 6.
Okay.
So look in the direction pi 6 or negative pi 6, it should be, but it doesn't matter, I go in both directions. I think the tangent of that angle pi 6 is going to be 1/√3. And isn't the tangent of an angle just a slope?
So
Here's the x-axis.
just why again are we taking the tangent?
Well, because look at this line.
Yeah.
It's got a certain slope, which is a ratio of rise to run, isn't it?
Yeah.
So y over x. But if here's my angle theta, I think the ratio of y to x is just the tangent of an angle. Tangents are slopes.
Okay. Yeah.
So you guys help me with this. Have we talked about reflective qualities of parabolas?
Yes. Yes.
Have we talked about reflective qualities of ellipses?
No. Or yes. Yes.
But this is our session.
No.
Horrible ellipse, I'm sorry. Let me do that one more time. An ellipse has two foci. And if you stand at one focal point and throw a projectile in any direction your arm will please, you'll hit the elliptical reflector, it tends towards the other focal point. Point in this direction, hit the elliptical reflector, tends straight towards the other focal point. Nice applications. Here's a human body.
Catch it in space.
And in this human body, I've got something on the inside I want to destroy, but as a surgeon, I just don't want to cut through the human tissue. And so a form of laser surgery really operates on this reflective quality of an ellipse. Put a small bathtub outside the human body, and from one of the focal points, I will emit sonic waves in all directions. As a surgeon, I'm using a computer to identify the location of the object I want to destroy in the human body, but once I send out all these sonic waves, sound waves, not light waves, they're basically useless. So when they hit the elliptical reflector, they pass through the human tissue, still being so darn weak they don't do any damage at all. Until they're concentrated at the other focal point where they're strong enough, they can perhaps break this object into smaller parts, so the human body can just naturally flesh out the remnants. Typical applications, kidney stones.
So what happened to this person to make him look like that?
Oh, be quiet.
He's dead now. Look, there's a car.
It didn't work.
Why can't you do this? Well, isn't that like why can't you do that with a parabola? Actually, with a parabola is the same thing.
I disagree, because I think with the parabola, from that focal point, you throw something in any direction you please. What happens is they reflect off and run parallel to the central line of symmetry. And so you get this wide beam. Not a bunch of rays coming into a single point elsewhere.
So that's how you make a death ray?
What's that?
I was thinking if you were going the other way, but you can't do that.
Okay, you guys, my last application. Please don't embarrass me with my age. Who fought in the Battle of Britain? The Great Battle of Britain?
The British?
Well, yeah, well.
French.
No, not the French. You guys,
Russians, no.
Doesn't matter.
in between the French and Russians, geographically speaking. The Germans. The Battle of Britain, just before we entered World War II.
That's
Right.
not
Sure, that was.
Gee.
I remember that, yeah.
And it was a time where the Germans basically conquered everything in the European theater. And again, just before the Americans got into the war. And the reason why the Germans conquered everything is they were
Loud.
They were Germans. They were really smart. They were more advanced than anybody else with technology. And they developed, among other things, aircraft that just decimated everybody else's Air Force. They decided to leave the English for last. And the Battle of Britain was to do nothing more than to bring down the Royal Air Force of Great Britain. And Great Britain knew they were doomed. Because they had no aircraft just like anybody else in the world that can defend themselves from the Germans, particularly their German Luftwaffe, their Air Force, and where they had something called the Messerschmitt Me-109. But there is an Englishman who decided, before invasion, that if he can just simply design an aircraft whose front wing was elliptical, for the most part, actually a little bit shaped off the front, but mostly elliptical, then he determined that this particular aircraft would have at least aerodynamic capabilities good enough to keep and fight with the German fighter aircraft. So he went to Parliament, said, "Can I have funding to develop this aircraft?" And they laughed at him. This aircraft cost 2.5 times the amount of money it cost to build a current fighter at the time, and they said, "We can't afford it." But there was more discussion. They knew an invasion was imminent, or at least an attack of their Air Force was imminent by the Luftwaffe, and they finally said, "Okay, fine, we'll fund partially this aircraft." And they built it. And because this aircraft was built was the only reason the British were able to fend off the Luftwaffe just in time for the Luftwaffe to say, "We give up. It's not worth our fight. We've got another eastern front with the Russians. We give up. We'll stop trying to conquer England." Since they didn't know what the name of the aircraft is.
Spitfire.
Yeah, the Superman Spitfire. The Americans loved the idea, so the Americans built the... Well, the P-51 Mustang had the same engine. Kinda. We're Americans, so we bored out the cylinders, made it look larger, more powerful. But the Americans stole the idea of this wing and built the Thunderbolt.
So what was so good about the wing?
Now, this may not be an example of the reflected quality of the limbs, but certainly like two great examples where mathematics completely saved the Allies in World War II. Building this plane with elliptical wings finally gave us, as allies, an aircraft that could fend against the Germans.
But why? Like, I get it's an elliptical and it worked well, but
You know, this particular engineer simply played with the idea of the wing and found it did have really nice aerodynamic capabilities, had more control over maneuverability. And if you look at this kind of wing compared to other airplanes at the time, have much greater surface area. They modified it a lot. In World War II, they experimented with pointing at the tips. Allowed to have those capabilities at higher elevations, things like that.
So did he end up drawing math equations in dirt as well?
Actually, I don't know about this particular engineer. You know, the Germans, they figured out some flaws in this aircraft, like every Allied aircraft. You guys know what a carburetor is? Do you? Because I assume you guys have cars that don't have carburetors. It's an object that mixes fuel and oxygen. And the Germans realized, the British, just so far behind, they've got carburetors. The Germans didn't. They had fuel injection. Yes, they had fuel injection. I'm talking 1940. And so they realized if they were being chased by a Spitfire, all they had to do is pull some serious G's. And the Spitfire behind them would try to follow, but of course the G's wouldn't allow the fuel to go through the carburetor into the piston chambers. So they figured out ways around. Okay, I'll stop talking. You guys, I know I didn't do anything serious the past half hour. I just wanted to give you a few examples of sketching graphs of conic sections when you're given the polar representations equations. So if you guys don't mind, just a tiny, tiny bit of practice with those. No calculus involved, just practice.
For the exam tomorrow?
Yes, I
are we
saved this
gonna be
stuff.
doing calculus on
Yes.
this section on the exam?
I'll certainly have you do calculus on parametric curves, just not necessarily the conic sections.
But that's just to prepare us for next semester. I mean, what was the point of?
You'll end up rotating these, around the axes. and get
Yeah,
higher dimensional objects.
I gotta confess, you guys, in 3-space, there are many instances where it's cumbersome to talk about a surface in 3-space using rectangular coordinates. So next semester, we will start talking about surfaces graphed in terms of, we don't really call them polar coordinates, but they are polar coordinates. We'll call them cylindrical coordinates. And maybe even a whole new way of doing things, so that they're called spherical coordinates. It'll come back, I agree. Just not in the format you're seeing in this chapter. So can I talk about tomorrow since I can talk?
Oh, it'll be fun.
And can I jump around a little bit?
Let's.
So you guys, in chapter 10, for the most part, with parametric and polar graphs, I could be asking you things like, slopes of tangent lines, stuff like that. But when it comes to polar graphs, I can also talk about areas bounded. Then I think if I could walk backwards a little bit, I think the most important notions in chapter 9 are number 1, building a power series using what we know about geometric series. Building power series in the more traditional fashion, that's more universal. Maybe talk about error values along the way. And if you got an alternating series, jeepers, that's a piece of cake. It's the absolute value of the first unused term. I think going backwards, again, chapter 8, at least with what comes beyond sequences, you need to know those various different convergence tests, as well as the test for divergence. And I know I'm the professor, I know you're tired of me saying this, I just don't think there's a lot there. You can laugh. You can smile.
Actually, your exam from last year looked pretty nice.
Oh, was it really?
Yeah,
I
it
really
was-
did
it
not
was
look
pretty
at it.
nice.
You guys asked me to post things, I did. I didn't take a peek.
Yeah,
I love your
yeah, I
solutions.
like the.
My solutions.
Yeah, just one problem. Solutions for it. So those were just problems.
I love how your solutions take like a couple lines and mine take like 3 or 4
Oh, I
pages.
see your point. I see your point. Okay.
Well, no, a lot of them were blank. There were no solutions.
Yeah, like,
Oh, you mean the other exams? You know what happened? I typed solutions on what was pertinent for exam 3, as I
Okay.
recall. I think that's what I did. And just didn't get the other ones.
Can you say what's,
Yes.
can you talk about chapter 9 again?
Yes, I can. I think chapter 9, here's the 2 real big ones. The biggest guns are building a power series with what we know about geometric series. Building a power series in a more general form. And then also, I have to confess, dealing with error values when you use Taylor polynomials to approximate something, like 1/√5.
And you said there was one more last thing you said.
Then back in chapter 8,
Alternatives. Yeah.
take a peek at, I did say, in terms of errors, if you got an alternating series, choose the easy route. Look at the absolute value of the first unused term. That'll give you an upper bound on error. Now, as far as the rest of the course is concerned, that is to say, Thursday's exam, you guys, I gotta confess, almost all of it's just integration. I mean, it really is just integration.
The physical applications, though, I mean, we can.
You should expect with physical applications, because I really want to test you on integrating, you should expect those applications for me to ask you to set things up.
Okay, so we should check all those, or like, would there be any particular physical applications that we should study more than others?
Is there?
Yes. Force due to hydrostatic pressure,
Okay,
work, and volumes.
okay. So all of them?
Oh, and our
So are we hanging our commutes off a chain again?
Yeah, if we do it in polite fashion where it doesn't scare him, yes. We want to be nice to our kids.
That wasn't.
Yeah, Archimedes has it rough, I gotta say. He's hanging from chains and, yeah.
Chased by reptiles.
Yeah.
That wasn't his fault. Can I just tell you guys right now some things I did not put in the exam? The exam's already been out to printers.
Okay,
I didn't put anything from section 6.1, velocity and net change.
okay.
I know it was on your first exam, but I just didn't put anything on the final. I didn't consider section 6.2 regions between curves because I can incorporate that with points. I'm sorry I'm so slow, just a minute. That's all I can think of. That's all I can think of.
And there's no 8.2 still, right?
You know, I have to confess, I didn't put anything in terms of sequences on these names, as I recall.
Okay.
Yeah.
But we get all that in the power series anyways. I mean, technically, power series.
You know, technically
in fact,
speaking, in
is
terms of
sequence.
finding a pattern,
Yeah.
which is what we play with in terms of sequences, that's true, that's true.
So are you gonna be in the math center all day today?
You know, I might sneak out for a quick lunch.
Okay.
Just a quick lunch. I know I have to run to the library real quick some other time today.
Are there any groups that belong on the Thursday test?
Only in terms of,
Infinite?
no.
Proofs at all.
No limit proofs?
What? Well,
That's
I
my
was looking
favorite
forward
part.
to
though.
those.
That's-
I think this final I didn't put anything in proofs.
Numerical integration.
Oh, yeah, that's fair game. But don't memorize those error formulas. Again, I'll give those to you if you need it.
What about, differential equation word problems?
Yes, that is definitely fair game. Definitely.
That would be on Thursday's test.
Yes, not tomorrow, so it'll be on Thursdays. You said the new stuff tomorrow, right?
Yes.
Mhm.
Well, once you get the old stuff.
Well, yeah, tomorrow we come in, it's just,
All this studying.
Gosh, I wonder if it's just gonna be this few of us tomorrow. Well, one of us walk out today.
yeah.
Oh, I'm sure he's moving.
All right, you guys are around.
Okay.
If I leave, I'll be there.